then as you can see, the equation over here is calcium solid plus 2H2O liquid gives CaOH2 aqueous plus H2 gas. And then we have magnesium. It has a very slow reaction, but it has a vigorous reaction with steam. It glows brightly. Hydrogen and solid magnesium oxide form. This happens when it is reacted with steam. Notice the change of state symbol over here. It is Mg solid plus H2O gas gives MgO solid plus H2 gas. Then we move on to the reaction of metals with dilute hydrochloric acid. Over here you can see magnesium, magnesium having a vigorous reaction, and this is over here, but by the way, it is magnesium solid plus 2HCl aqueous, which gives magnesium chloride aqueous plus H2 gas. Then we have zinc, and the reaction is quite slow with dilute HCl. Here we have Zn solid plus 2HCl aqueous, which gives ZnCl2 aqueous plus H2 gas. And then we have iron, which has a slow reaction with dilute HCl. That is iron solid plus 2HCl aqueous, which gives FeCl2 aqueous plus H2 gas. And then we have copper, silver and gold. They have no reaction at all, even with concentrated acid. Moving on to reactions of metal with oxygen. So here is sodium. It burns vigorously with a yellow flame. And here you can see the reaction, which is 4Na plus O2 gives 2Na2O, which is the white solid. And here you can see the yellow flame. And then we have calcium, which burns vigorously on strong heating with an orange-red flame. And we have magnesium, which burns readily with a brilliant white light. Iron, which burns readily with bright sparks when iron filings are used. And copper, which reacts slowly at the surface, and a black coat is formed. You can see there's a black coat over here, which is 2CuO. This is the reaction of magnesium. This is the reaction of calcium. Now we look at the reactivity series. Firstly, we have potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, copper, mercury, silver and gold. So as we go down, let's assume that this is below this, or I can just write it a bit smaller. I'll just clear this up. We start from the top. We have K, Na, Ca, Mg, Al, Zn, iron, tin, lead, copper, mercury, silver and gold. So as we go down the reactivity series, the reactivity decreases. This being the most reactive, this being the least reactive. Now we look at the important points. Firstly, more reactivity means higher drive of giving up electrons to form positive ions. And then more reactive metal more reactive metal will displace less reactive metal. Displace means that it will take the place of the less reactive metal, which we'll look ahead. And then thirdly, more reactive metals are harder to extract. And lastly, less reactive metals less readily form compounds. The least reactive metals, which are gold, silver, and copper, they are found as elements in the Earth's crust. Now we look at competition with carbon. So let's assume that we have a crucible over here. Over here we have a mixture of magnesium oxide, which is heated with carbon. Let's assume that these dots, the yellow dots are magnesium oxide and the blue dots are carbon. So is there any reaction? No, there is no reaction. Meanwhile, in another crucible, we heat up copper 2 oxide and carbon. So as you can see over here, beads of molten copper will be formed, as copper is less reactive than carbon, so it has been displaced. So the overall reaction here, it is 2CuOS plus CS gives us 2 copper S plus CO2 gas. So as you can see, copper has been displaced by carbon in the second crucible. Now we move on to competing with other metals for oxygen. So let us assume that over here in this crucible we have powdered iron, which is heated with copper 2 oxide. This yellow is iron and red is a copper 2 oxide. Here we have heat. So can iron displace copper from copper 2 oxide? Yes, it can, since it is above in the reactivity series. So once the reaction starts, it gives out heat and iron 2 oxide and copper will form. So the reaction goes over here. You can see that copper has once again been displaced from its position by iron. Thirdly, we look at competing to form ions in solution. So over here we have a beaker. Here we have our water, which is actually copper 2 sulfate. We actually have copper 2 sulfate over here, and in which we place an iron nail. So do you think that copper will be displaced from copper 2 sulfate by iron? Yes, it will be. So what will happen here is that this blue solution, which was over here, will now become pale green. And on the iron nail, severe coating of copper. So the reaction for this will be iron as solid, the CuSO4 as aqueous, which gives us FeSO4 aqueous, the Cu solid. Now again we have some points to note. And firstly, carbon is more reactive than some metals and will reduce the oxides to the metal. Metal will reduce the oxide of a less reactive metal. Reduction is exothermic and metal oxidizes itself. A metal displaces a less reactive metal in solutions of its compounds, and a more reactive metal loses electrons more readily to form positive ions. Now we move on to metal extraction. When we talk metal extraction, we talk ores. Ores are rocks from which one obtains metals. When metal occurs as an element, it is separated from impurities. And when metal occurs as a compound, reduction is required. Here you can see we have put an image over here from the textbook. So according to the reactivity series, these are the reactions used to extract the metal from the ore. So for potassium, sodium, calcium, magnesium and aluminium, we use electrolysis. For anything below carbon, zinc, iron and copper, we use heating in a furnace with carbon and carbon monoxide. And for silver and gold, they occur naturally as elements, so reduction is not needed. Now we can see as we go above, the method of extraction is more powerful and the method of extraction is more expensive, as ores are more difficult to decompose and metals are more reactive. Now we look at iron extraction. So the mixture containing iron ore is called a charge. So charge has iron ore, which in this case is hematite. We have limestone and we have coke, which is basically carbon, an allotrope of carbon. Here we can see the blast furnace. In the hopper, the charge is loaded with this charge, and then waste gases are out, and they are used to heat up the air blast. Over here at 400 degrees Celsius, the iron forms and trickles down, and at 800 degrees Celsius, carbon monoxide forms and rises, and at 1400 degrees Celsius, carbon dioxide forms and rises. From here, hot air is inserted, and even from here, hot air is inserted. This is the plug hole. This is important slag, which is an impurity, and this is another plug hole for the molten iron to come out. Now we look at the reactions in the blast furnace. So firstly, coke burns to give off carbon dioxide and heat. The blast of hot air makes coke burn, and it is highly exothermic redox reaction. So the first reaction goes carbon as solid, which is a coke, plus oxygen gas gives us CO2, which is gas. The second reaction is that carbon dioxide is reduced to carbon monoxide. Carbon monoxide reacts with more coke, and the reduction is endothermic. And carbon solid, CO2 gas, there's 2CO, which is gas. And the third reaction is that carbon monoxide reduces iron 3 oxide to iron. So extraction of metal occurs, and this again is a redox reaction. So Fe2O3 solid is 3CO gas gives 2Fe liquid is 3CO2 gas. And the fourth reaction is the decomposition of CaCO3 due to form CaO and CO2. So we have CaCO3 to decompose to CaO a solid and CO2 a gas. And the last reaction is the reaction of calcium oxide with silicon 4 oxide. So CaO plus SiO2 gives CaSiO3, which is known as slag. These are the 5 reactions. We need to learn this by heart. Then moving on to the rusting of iron. Oh, before that I forgot to mention that the waste gases exit from the top of the furnace, as we have seen, and heat from them is used to heat the incoming blast of air. And the molten iron containing carbon and some sand. Some is used to make brittle cast iron, which has high carbon content, and most of it is turned to steels, which is an alloy, which we'll see later in this chapter. Now we move on to rusting of iron. So rusting requires oxygen and water. So the reaction for rusting, very important, is 4Fe solid plus 3O2 gas plus 4H2O liquid gives us 2Fe2O3 hydrated 5H2O. And these are a few ways to prevent rusting. One is paint, second is grease, third is plastic coating, and we have galvanizing. So galvanizing is basically coating with zinc. Then we have electroplating with tin. And then we have sacrificial protection. In sacrificial protection, another metal will be oxidized instead of iron. For example, magnesium or zinc. Now we move on to extracting aluminium. So the ore is bauxite, and aluminium is extracted by the electrolysis of aluminium oxide using carbon electrodes. Here is the electrolysis. It is carried out in a steel cell lined with carbon cathode. The anodes are hanging. The aluminium oxide is dissolved in cryolite or sodium aluminum fluoride, but usually in exam it is dissolved in cryolite. We have to mention cryolite. So firstly, it reduces operating temperature to 1012 degrees Celsius, which we need not mention, and the solution becomes a better conductor than aluminum oxide. And then we start by observing the reactions at the electrodes. So at the cathode, the reaction is 4Al3 plus. I'll just erase this, give me a moment. Okay. So the reaction at cathode, which is a negative electrode, is 4Al3 plus, which is liquid, plus 12E minus, which gives us 4Al liquid. If this is a reduction reaction, then at anode, the positive electrode, we have 6O2 minus liquid, plus, which is formed by 3O2 gas plus 12 E minus. This is an oxidation reaction, and the overall reaction is aluminium oxide forms aluminium plus oxygen is 2Al2O3, giving us 4Al plus 3O2 gas. And also one more thing to mention is that aluminium, although it's highly reactive, it does not really react with the atmosphere because it already has a layer of aluminium oxide formed over it. Now we look at uses of aluminium. The first use is overhead electricity cables. That is because it is a good conductor of electricity, it has low density, it is ductile, and it resists corrosion. Second use is cooking foil, food containers, and drink cans. Because it has low density, it is non-toxic, it resists heat and corrosion, it can be rolled into thin sheets, meaning it is malleable. A third use is in aircraft. This is because it has low density and it resists corrosion. Now we move on to use of copper. So the first use is electrical wiring. Because it is one of the best conductors of electricity and it is ductile. And it is also used for pipes because it is malleable so that the pipes are easy to bend, it does not readily corrode, and it is non-toxic. Then we move to uses of zinc. So firstly, it is used to coat or galvanize iron and steel. Because it prevents rusting through sacrificial protection and also by keeping air and moisture out. And then it is used for torch batteries. Because it gives a current when connected to carbon electrode in a paste of electrolyte. Now we shall move on to alloys. So an alloy is a mixture of a metal with at least one other element. So turning metals into alloy changes its properties and makes it more useful. Some examples are mild steel, stainless steel, and brass. Now we'll look at how alloys work. Firstly, this is what an alloy looks like. So this is what an alloy looks like. Firstly, new atoms must enter the metal lattice. The main metal is melted and the right amount of new element is dissolved. Solution is cooled and hardened. New atoms may be larger and smaller or smaller than main metal atoms, and there is a change in strength and more corrosion resistance. There is also a change in conductivity and appearance. You can add more than one element. So basically, particles in alloy prevent layers of metal ions from sliding over each other. Now we look at brass. So brass is copper and zinc. Its special properties: it is harder than copper, it is attractive, and it is non-corrosive. Its uses are musical instruments, ornaments, and doorknobs. Now we move on to bronze. Bronze is copper plus tin. Special properties are it is hard, it is sonorous, and is non-corrosive. Its uses are coins, statues, bells, ship propellers. Then we move on to typical stainless steel, which is iron, is chromium, plus nickel, is carbon, and other elements. Its special properties are it is strong, it is non-corrosive, and it is attractive. Some uses include cutlery, utensils, construction, and medical equipment. Now we look at a typical aluminium alloy, which is aluminium plus zinc plus magnesium plus copper. Its special properties are it is light, it is strong, and it is non-corrosive. Some of its uses are aircraft and spacecraft. Thank you.